I want to look a little bit more closely at the convergence of these methods we've been speaking about, both with respect to a generic fixed point method and also in particular to Newton's method. So as you'll remember, a generic fixed point method, it involves some fixed point function. Given some initial estimate for the fixed point, we generate new estimates by feeding the old estimate into the fixed point function g. The analysis that we've done so far typically says that if the absolute value of the derivative of g at the fixed point is smaller than 1 in absolute value, and that derivative is continuous near the fixed point, and your initial x1 is a reasonably good approximation to the fixed point, then to put the matter mildly, it's going to work. Now, Newton is a special case of a fixed point method. Newton's method is the new iterate is the old one minus the function value at the old one divided by the derivative of f at the old one. We are assuming for the moment that we never encounter places where f prime at xk is 0. We will have to investigate the ramifications of that later. G of x, if I'm thinking of Newton as being a fixed point method, must be x minus f of x over f prime of x. R being a fixed point of g, that is, r equal g of r, in this Newton method is equivalent to r equals r minus f of r over f prime of r. Subtract the r's away, and it turns out that obtaining a fixed point of this g function is equivalent to finding a 0 of the f function, which is the problem that we're really interested in. Since the error at step number k plus 1 is the absolute value of g prime alpha times the error at step k, alpha being between the solution r and x number k, we previously discussed that if this derivative is always less than 1, we get improvement. The error at the next step is less than the error at the previous step. There's a technical point which I'm going to avoid for now, but the actual desired formulation is we'd like the size of the derivative to be no more than some number L, which is less than 1. This prevents this absolute value of g prime from approaching 1 and causing the convergence to become even slower than it's going to be. We'll look at an example of this later. If this is the case, then our fixed point iteration is going to obey the error at the new iteration is less than or equal to some constant L times x minus r to the first power. We call this first order convergence or linear convergence. In the world of numerical methods, linear convergence is the minimum that you're willing to accept. If it's not even linearly convergent, then people generally regard a method as not being any good. Now, in Newton's method, if I calculate the derivative of the g function, the derivative of x with respect to x is 1, and to do the derivative of f of x over f prime x, I do the quotient rule, which works out to be this. If you are at a fixed point, if x is equal to r, that is to say, you're at a place where f of r is 0, something very interesting happens. G prime at r, 1 minus this fraction, but this factor is 0. So the second term in the fraction upstairs is 0. G prime at r is 1 minus something divided by itself, which is 1 minus 1, which is 0. So as we've seen before, Newton's method under these circumstances is excellent. G prime at the solution is as far from having absolute value 1 as you can manage and still be within the range of G prime values that will give a convergence. We are all supposed to have had at least through calculus 2, so I'm just going to state Taylor's theorem with remainder here. If I have a function g which has continuous first through n plus first derivatives, then I can write g of x as g of c plus g prime of c x minus c plus 1 over 2 factorial times second derivative of g at c x minus c squared, and so on and so forth, out to the term that has the nth derivative in it, plus the remainder term, which is 1 over n plus 1 factorial times the n plus first derivative of g evaluated at some number alpha multiplied by x minus c raised to the n plus 1 power. And all I know about the alpha is it's between the place I'm evaluating g at and the center of my polynomial expansion. I'm going to expand my g function about x equal r. Now, at this moment, r is just a letter. In a moment, I'm going to think of this as being a fixed point, but for now, r is just a number. I'm going to expand out to the first order derivative multiplied by a power of x minus r, and then the error term that goes with that polynomial. So g of x is g of r plus g prime at r times x minus r, plus 1 over 2 factorial times the second derivative of g evaluated at alpha multiplied by x minus r squared. Now, this statement, this one at the top of the page, is sort of generically true as long as g has up to a continuous second derivative. But if we're doing fixed point iteration, I'm going to evaluate this formula at x equal x number k and find out that g at xk it's the same formula again, except every place where I've written down the letter x previously, I write down x number k now. And since it may vary from iterate to iterate, I'll label alpha as being alpha number k as well. That's not as troubling as it looks. If we're close to x equal r, and the second derivative is continuous, then the second derivative of g at alpha number k will be very close to the second derivative of g at r because of the continuity. But the way we do fixed point iteration is we take x number k, feed it through the g function, and call that x number k plus 1. So that becomes x number k plus 1. If r is a fixed point of g, then g of r is r. So I'll just write that down. And then the rest of this stuff I just write down. If xk is at all a good estimate of r, then xk minus r will be small. When I square x minus k, that must be very small. I just mentioned that g double prime of alpha k is not very troubling to me. So in the generic fixed point iteration, if I'm at all close to the solution, this term is extremely small compared to this term, and for all practical purposes, I can ignore it. This is, roughly speaking, the kind of behavior we've already seen to expect from a fixed point method. But we've already seen that if we're doing Newton in the nice case, where f of r is 0, but f prime of r is non-zero, then g prime at r comes up equal to 0, and then that term that dominated the behavior in a generic fixed point method is 0, and only the last term remains. So if we are doing Newton in the favorable situation, xk plus 1 minus r is some number that's roughly 1/2 times the second derivative of g at r, not times the error at step number k, times the square of the error at step number k. Because of the 2, the second power, we call this kind of convergence quadratic convergence. And here I've written out in symbols what I just said verbally. I want to take just a moment to make a side comment. Let's say we're trying to compute some number. It has an exact value, and we approximate some sort of approximation to it. We defined the relative error to be absolute value of the approximate minus exact divided by the absolute value of the exact error. We also interpreted this to mean this: if that number, for example, were to come up 10 to the negative 8, we would say that the approximate and exact answer agree to about 8 significant figures. And what I want to talk about very briefly here is how to express symbolically the number of significant figures that the approximate and the exact quantities agree with. If you take the base 10 logarithm of both sides, you'll get the second formula. The quantity over on the right side is the number of significant digits, except it's got the wrong sign on it. The number of significant digits is the negative of the logarithm of absolute approximate minus exact over absolute exact. This is a way of somewhat formalizing what we mean to say we have a certain number of significant digits correct. Let's think about significant digits in relation to generic fixed point methods. So I'm going to do my fixed point method. As we stated multiple times, the error goes like this. If I'm close to the solution, the error is roughly absolute g prime at r times the error at the previous step. If we have absolute value of g prime of r less than 1, I should have my technical point here, but I'm just being loose in my language, less than or equal to 1, then close to the solution, this error formula that we have has this coefficient out front less than 1, and that's going to let me figure something out. Divide both sides of that relationship by the absolute value of r, r being the fixed point, the exact value that you're after. This number is still less than 1 in magnitude. How am I going to talk about digits as compared to relative error? I'm going to take the relative error, I'm going to take the base 10 logarithm of that, and then I'm going to put a negative sign in front of it. So this is approximately equal to this. Take the logarithm of both sides and put a negative sign in front, and you'll get the equation in the middle of the page. This literally represents the number of correct digits in x number k plus 1. This one, we have to do a little bit of work. In the face-to-face class this morning, there was a bit of confusion about what I was doing. I looked back on it All that was going on was that I skipped a step and a half of algebra. So let me be explicit here. Negative of, I put the rest of it inside brackets. The logarithm of something times something else is the logarithm of the first one plus the logarithm of the second one. In a moment, on the next page, I'll distribute the minus sign through. So the number of correct digits in x number k plus 1 is the negative of the logarithm of absolute value of g prime of r plus, and I've written this in the format that I have because it means something to me. I could have just said minus the logarithm of all of this stuff, but I prefer to write it as plus the negative of the logarithm of all of this stuff. The reason for that is this quantity inside the square brackets is the number of significant figures in x number k. So the number of digits that's right in x number k plus 1 is the number of digits that was correct in x number k plus the negative of the logarithm of the absolute value of g prime of r. Now, at first glance, that's very troubling because it looks like I'm taking the number of digits that were correct in x number k and adding in a negative number, which would be a disaster. That would mean my new x is less accurate than my old x, but this is an optical illusion. The absolute value of g prime of r is less than 1. In this nice case where I have convergence, the logarithm of that is negative. So the negative of the logarithm of absolute g prime of r is the negative of a negative number, and so is positive. So this negative sign is not a worry. It just looks like it might cause trouble, but in point of fact, it doesn't. The number of digits in xk plus 1 is the number of digits in xk plus this number, which does not depend on k. What this means is every time I do a step of Newton's method, or in this case, a generic fixed point method, that is, I'm going to gain the same number of digits. If this number somehow worked out to be 7, then every time I do, excuse me, every time I do a step of the fixed point method, I would gain 7 digits of accuracy. That would be excellent, but usually it doesn't happen like that. If this number was 1/3, which is far more typical, every time I do a step of the fixed point method, I'll earn 1/3 of a digit more in accuracy, which means, roughly speaking, to get one additional digit, I'll have to do 3 steps of the fixed point method, and that's not very good. So now I'm ready to think about Newton's method. In Newton's method, in the agreeable situation, the error at the new step is roughly given by this formula. Divide through by absolute value of r, and now I have a problem here. I want to relate the relative errors between the two iterations. This is going to be the relative error in x number k plus 1, but see, this isn't right. I've got a second power on the absolute xk minus r. If I had a second power on the r, then I would be all right, because I could write this chunk as the square of the relative error at step number k. So I'm going to do a simple algebra trick. I say to myself, I wish this said absolute value of r squared here. So I'll just stick in an extra factor of absolute value of r on the bottom and put a factor of absolute value of r up here so that one could cancel them out if you wanted to, which we don't because I like the way this looks now. This last fraction is the square of the relative error at step number k. Having done that, we can do exactly the same negative of logarithm of quantity trick that we did before, and we find out that the number of correct digits at x number k plus 1 is this quantity, which doesn't depend on k, and therefore I'm not going to worry about it very much, plus this part, which I am going to be very interested in. The number of digits that are correct in x number k plus 1 using properties of logarithms is that term that I'm not going to worry very much about. The logarithm of a quantity squared is 2 times the logarithm of the quantity squared. When I did lose a minus sign there that I had before. The number of digits correct at step k plus 1 is this constant that I'm not going to worry about, plus twice the number of digits that were correct in x number k. Roughly speaking, this says that the number of digits that are correct in x number k plus 1 is twice how many digits you had at x number k, and this is excellent. Continuing to not worry about that first term too much, suppose your x1 was close enough to r so that you had one significant figure of agreement. Say the approximate answer was 1.7 some odd, and the true answer was 1.45 some odd. At step 1, you have one digit correct. At step 2, that doubles, and now you have 2. At step 3, that doubles again, and now you have 4. At step 4, you'll have 8 digits correct, and at step 5, you'll have 16 digits correct, which, as we know now, is approximately full double precision accuracy. Once your iterates get close enough to the true solution in the nice case for Newton's method, you're going to get extremely rapid convergence. The number of digits that are correct are going to double every single time you do a step of Newton, and this adequately explains why Newton's method is as good as it is. Of course, I keep saying in the nice case for Newton, so you know sooner or later it's not going to be so nice. Suppose that f of r is 0. So I've got a solution to the equation f of x equals 0. We say that r is a root of multiplicity m if m is the largest positive integer, so that when I calculate this limit, number 1, I don't get 0 for an answer, and number 2, the answer is finite. I don't get the plus infinity symbol or anything like that. We'll talk about what this means in a minute. But first, the nice case, if the multiplicity is 1, then this says that f of r is 0, and also the limit as x tends to r of f of x over x minus r to the 1 power is a finite non-zero number. If you put in an extra factor of x minus r on the bottom, that turns into something whose numerator approaches a and denominator approaches 0. And since a is not 0, that limit doesn't exist. We call such a root a simple root. A root of multiplicity 1 is a simple root, and the interpretation we're going to have for that is since f of r equals 0, this limit is the same as the limit as x goes to r of f of x minus f of r, since this is 0, divided by x minus r. This is the change in the y-coordinate on the graph of f. This is the change in the x-coordinate. The limit as x approaches r, as the difference of the x's tends to 0, is the derivative of r. F with, excuse me, is the derivative of f evaluated at r. Multiplicity 1 means f of r is 0, but f prime of r is not 0. So what that tells me is the nice case that I keep talking about is when I have a root of multiplicity 1. If the nice case is multiplicity 1, multiplicity 2 or higher naturally will be bad in some sense. Before analyzing the behavior of Newton's method in the presence of a root of multiplicity larger than 1, I feel like I really should look at an example. F of x equals x minus sine x. Obviously, 0 is a solution of f of x equals 0, because f of 0 is 0 minus sine 0, which is 0. Is the multiplicity of the root r equals 0, 1? So we calculate the limit of f of x over x minus 0, that's the x minus r, raised to the 1 power as x approaches 0. This is the limit as x goes to 0 of x minus sine x divided by x. As x approaches 0, both the numerator and the denominator of that fraction approach 0. That makes it an indeterminate form of type 0 over 0, meaning that we can use L'Hopital's rule on it. I can write down another limit whose top is the derivative of x minus sine x, and whose bottom is the derivative of x, and those two limits act the same. So I'll take derivative of x is 1 minus derivative of sine x is cosine x. On the bottom of the fraction, derivative of x is 1. Now this is not an indeterminate form anymore. This is the limit as x goes to 0 of 1 minus cosine x. Cosine x is continuous, so that means it's safe to just plug x equals 0 in, and you end up with 1 minus cosine 0, which is 1 minus 1, which is 0. This is not a root of multiplicity 1. It's not a simple root. It's not one of those situations where Newton's method is going to do good. Well, if it wasn't 1, maybe it's 2. This time, the power on the x minus r, the x minus 0, is 2 instead of 1, but still the top tends to 0, the bottom tends to 0, so I do L'Hopital's rule to it. The top of the fraction is 1 minus cosine x. As x approaches 0, that approaches 1 minus 1, which is 0. But unfortunately, the bottom of the fraction approaches 0 as well. This is still an indeterminate form of type 0 over 0. So I have to do L'Hopital's rule to it again. The derivative of 1 is 0. The derivative of minus cosine x is sine x. Derivative of 2x is 2. This is now not an indeterminate form. I need to take the limit of 1/2 of sine x as x tends to 0. sine x is continuous, it's safe to plug the 0 in. The sine of 0 is 0, half of that's 0. If I look at the m equal 2 situation, the limit comes up 0. I need this limit to be non-zero and finite, and the m equal 1 and m equal 2 have not done the job for me. So not to belabor the point, try m equal 3, and then a miracle happens. You get 1/6 for an answer. This is finite and it's not 0, but is it the biggest whole number that this limit's going to come up finite and not 0? If you try m equal 4 or m equal 5 or any higher power, you find out that the limit doesn't exist. Therefore, the root that we're looking at is a root of multiplicity 3. If I have a root of multiplicity m, then the limit of this quantity as x approaches r is exactly equal to a, where a is some constant. This means if I'm close to x equal r, then this fraction has to approximately equal a. So the meaning of this multiplicity in a non-algebraic way is that if I'm close to the solution, and if I have a root of multiplicity m, this means the function looks very much like this function, and we know all about the shapes of those kind of graphs from algebra. I can get insight into how Newton is going to act in the presence of a root of multiplicity bigger than 1 by analyzing the function that f looks like. I can pretend that f of x is a times x minus r to the m. If I figure out how Newton's method acts on that sample problem, I'll have a good estimate for how Newton acts in the presence of some other type of function that has a root of multiplicity, like x minus sine x, for instance. Well, it isn't good. The function that I'm examining is a multiplied by x minus r to the m. So this top of this fraction is the function value, f at xk. The derivative of that is, this is a constant. This is x minus r to the m power. The derivative is m times x minus r to the next lower power, and then I have to evaluate that at xk. So this is literally Newton's method on my trial function here. The a's actually cancel out, so it doesn't matter what a is. I'm going to have an m in the denominator of this fraction, so I'll write that as a factor of 1 over m. Here I've got m factors of xk minus r, while on the bottom I have one less factor of xk minus r. Cancel out everything you can cancel out, and you'll have one left over upstairs. I want to relate the errors. So I'm going to take this formula and I'm going to subtract r from both sides. Here I'll just have x number k plus 1 minus r. Over on the other side, I'm going to group the minus r with the xk. That's just algebra. What I'm going to do then is, out of this first piece and out of this second piece, factor out xk minus r, and I'll find out that the error at step k plus 1 is, in my trial problem, a number, a constant, times xk minus r. This is a disaster. This is linear convergence. This is first order convergence. If m was 2, this would be 1/2, And I'm getting back that same slow convergence that bisection had. We have lost quadratic convergence here. And the bigger the multiplicity, the worse that it is. If m was 10, this constant would be 1 minus 1/10, which is 9/10. The error at the step k plus 1 retains 90% of the error at step number k, and it's just going to become dreadfully slow. The presence of a root of multiplicity causes Newton's method to lose its quadratic convergence, which, as I said, is real bad. Friday, we will have our second both section online discussion. And what I think I'm going to talk about is some coding issues. And depending on how the time goes, we may look at a modification of the Newton method that at least can partially repair this multiple root business. But as a parting shot, I want to reiterate, it's not just Newton's method. All kinds of numerical methods tend to act really badly if you're trying to solve an equation and you've got a root of multiplicity. This is a generic problem that everybody in the numerical analysis business knows about. And so now you know about it too. I hope everyone has a good day. We'll talk again soon.